Hey guys, Miss Peterson here, and welcome to AP Physics Lecture 5-2, all about the magnetic force. In this lecture, we're going to be talking about how the magnetic force compares to the electric force and how charged particles move in those magnetic fields. We'll be putting those together to see how a mass spectrometer functions, and then look at the magnetic force on current carrying wires and apply that to the function of a motor. So let's get into it. Just as a reminder, the magnetic field will only exert a force on a moving charge, and that force is the magnetic force. It is QVB as long as that velocity is perpendicular to the magnetic field. If it's not, we use the cross product and do it that way. Also, just a reminder, it is in absolute values on your equation sheet, and we use our right-hand rule to determine that direction. So let's go ahead and apply this. So we have a proton, okay, moving with a speed of 1 times 10 to the 5th meters per second through Earth's magnetic field, which has a value of 55 microteslas. So that's 55 micro is times 10 to the negative 6. So times 10 to the negative 6 teslas at a particular location. When the proton moves eastward, the magnetic force acting on it is directed straight upward. And when it moves northward, there are no magnetic forces acting on it. Okay, determine the direction of the magnetic field and the strength of the magnetic force on it as it moves eastward. So a little bit confusing of a problem, mostly because of that word up. In AP, especially in electromagnetism, we are often going to be working in 3 dimensions. So up is a little bit misleading. Typically, we should use toward the top of the page or out of the page, but we're talking in the context of Earth. So it says that when it moves east, the force on it is directed straight upward. Up could mean toward the top of the page, or it could mean up and out of the page. But it also says when it moves northward, no magnetic forces on it. So northward, no magnetic forces acting on it. That tells us that when it moves northward, it's moving parallel to that magnetic field. So from that context, we can determine that up in this scenario means toward the top of the page. Okay, yeah. So when it moves northward, there are no magnetic forces acting on it. So if it moved north, there would be no magnetic force because the field is also in that direction. Okay. So that's the field. So the force, when it moves east, upward means out of the page. Yes, so upward means out of the page, okay? Because if we had the magnetic force pointing out of the page coming towards us, okay, remember we use that with a circle, then we use our right-hand rule. Velocities to the left, your F or the magnetic force finger is coming out of the page, okay? So make sure you're doing this in the plane of your computer screen or in the plane of your paper, wherever you're looking. So that force is coming out of the page and the magnetic field is directed upward, okay? I'm going to use blue for our magnetic field lines, but that tells us that the magnetic field was directed upward. If you use this thinking upward meant toward the top of the page, velocity would be there, your force would be toward the top of the page, and the magnetic field would be into the page. But if the magnetic field were into the page, it would still have a force on it when it moves northward. So we know that the magnetic field here, oops, I wrote FM, that is not, that is the magnetic field. The force is directed out of the page. So the magnetic field is toward the top of the page or directed northward, okay? So it's a proton, so we know it's charge. So we can just plug in straight into our formula, okay? We got the magnetic force equals Q. Q on a proton is 1.6 times 10 to the negative 19 coulombs times that velocity, 1 times 10 to the 5th meters per second, times the magnetic field strength at 55 microteslas, so times 10 to the negative 6 teslas. So you plug that all into your calculator, and you get a force of 8.8 times 10 to the negative 19 coulombs, or newtons, okay? Newtons. Yep. Okay, cool. Okay, cool. So, what if there were an electric field acting on that proton at that location? Okay, so if instead we had an electric field pointing up, so an electric field with a magnitude of 55 micro, we use newtons per coulomb typically for electric field strength. It doesn't have a one-word unit or its own unit. So we typically use that for the electric field. Electric force, you remember, is the field times the charge. So plugging in our numbers, we have 55 times 10 to the negative 6 times the charge, 1.6 times 10 to the negative 19 coulombs. And as you can see, because we don't have that velocity component, it's going to be a much smaller magnitude force. Okay. Yeah. Comes out to 2.56 times 10 to the negative, 8.8 times 10 to the negative 24 newtons. So that 5 magnitude difference because of that speed component. Okay. So when things are moving fast, that magnetic force becomes much, much stronger than the electric force. But you could see if it was moving really, really slowly or not moving at all, then the electric force would be stronger. Okay. Now, let's think about that proton moving in that field. We have that proton with that velocity. Now it's in a magnetic field of 0.1 Tesla, directed into the page. Calculate the force on the proton and sketch its path. Okay, well, first, let's use that right-hand rule again. Thumb in the direction of the velocity. The magnetic field is going into the page, so the force on it is directed straight upward. Okay, so we have the magnetic force on it directed upward. What will that do? Well, that will cause it to curve. Okay, so it's going to curve up in this magnetic field, okay, as long as that magnetic field is there. That magnetic force acts perpendicular, so causes it to turn. And then as it turns, okay, the magnetic force is always directed inward. It has a value in this problem of, okay, let's go ahead and see. It's moving perpendicular to the fields, so we can just use QVB. 10 times it's a proton, we know its speed, and now just 0.1 Teslas for a force of 1.6 times 10 to the negative 15 newtons. Okay. Now, what will be the radius of that path? Okay. Well, what do we call a force that's always directed inward? Okay. Centripetal. Okay. This proton will undergo centripetal acceleration. So we know that that magnetic force is its net force. So it's equal to its mass times that centripetal acceleration. So doing a little bit of derivation here, magnetic force is QVB, and then we have mass. Centripetal acceleration, if you look on your equation sheet or remember from AP Physics 1, is V squared over R. So the squared cancels out this V, and then we do a little algebra. Okay, R QB equals MV. Divide by QB, and we get that R equals MV over QB. Okay, and this is one of those equations that comes up a lot in the curriculum that's not on the equation sheet. It's a pretty straightforward derivation, but I recommend memorizing this one. So, how are those things applied? Okay, one of the main ones is a mass spectrometer. So a mass spectrometer is a device used in chemistry and in analysis of different compounds. Basically what it does is typically you have a sample that you want to know what it's made of. You ionize it, so you fire high energy particles at it to break it into pieces and give those pieces a charge. Then they go through here, which is a velocity selector. So let me explain how this works, okay? We have that Q right there, okay? I'm going to draw it over here. Q, it is a positive charge. Let's go ahead and find the direction of the, or first, electric field lines. The electric field, remember, always points from positive to negative, so that Q is going to be attracted to the negative. Positive charges flow with electric field lines. So we have the electric force pointing down. And then by our right-hand rule, magnetic field is going into the page, velocity is going to the right, so the magnetic force on it is directed straight up. Okay, so magnetic force is QVB, and electric force is EQ. They both have that Q dependence, okay, but only the magnetic force has the velocity dependence, and this allows us to select for a velocity. Okay, so electric force, nope, not electric field, electric force is the electric field strength times the charge. The magnetic force is QVB. So if we want them to pass through undeflected, okay, well, if it's going too fast, then the magnetic force becomes too high and it'll curve upward. Where if the speed is too slow, then the electric force, okay, would be more and it would curve downwards. So what we want is we want those forces to be equal, okay? We want the magnetic to equal the electric. So QVB equals QE. It's the same particle, so the Q's cancel. So the velocity it selects for is equal to that ratio of the electric field divided by that velocity. Okay, cool. That's how we can sort them by velocity and make sure that every single particle entering this second part of it has that same force, has that same magnetic force on them. Or, sorry, has the same speed. So if they have the same speed, the only thing that would affect the radius of this path, would be their mass. Okay, normally when we ionize them, we give them all the same charge. They're in the same magnetic fields. We use a velocity selector so they all have the same velocity. So then the radius of the path is the only thing, is only affected by the mass. Okay, so we can use where it hits this photographic plate, this our data collection thing. We can tell its mass from that position. Okay, and that's how a mass spectrometer works. Okay, let's look at an example of that. Okay, so say an electron is accelerated between two plates with a potential difference of 1,000 volts, as shown here. It passes through a hole in one of the plates and enters a magnetic field of 0.1 Tesla is directed into the page. Find the radius, the path the electron makes with the magnetic field. Okay, so first we're going to need to do a little bit of review here. We have our change in voltage, okay, and we have our magnetic field strength, and we know it's an electron. So I'm going to go ahead and write down the mass and charge on an electron from our equation sheets. thought it was negative 31. Couldn't remember if it was negative 31 or 32 kilograms. And its charge is 1.60 times 10 to the negative 19 coulombs. So, first off, we know we need to know how fast it's going. We need to know its speed at that point when it enters the field. So, this is a conservation of energy problem. Its electrical potential energy is being converted to kinetic energy. Okay? So, we know that. So we can use it to find its speed. Its change in potential energy is Q delta V. Yep, because remember, voltage is the energy per charge, so energy per coulomb. We multiply it by that, we get its energy. And then 1/2 mv squared. So do a little bit of algebra, and you get that the velocity will be equal to 2q delta v over m, and then the square root of that. Okay. So we plug that into our calculator. We have our q, we have our delta v, we have our m, and we get that it is moving with a speed of 1.87 times 10 to the 7th. So I'll go with 1.888 or 874. So 1.87 times 10 to the 7th meters per second. And then we can use that with our radius equation, mv over qb, to get our answer. So that's our v. Multiply it by our m, divided by q times b, and we get a radius of 1.07 times 10 to the negative 3 meters, which would be 10.7 centimeters. Right? Or 0.107 centimeters. That's 0.107. My brain is functioning this morning. That is just millimeters. Let's go with 1.07 millimeters. Okay, milli is times 10 to the negative 3. Okay, cool. Okay, cool. So, let's talk about particle accelerators. Okay? Any new physics news? We've discovered a new particle, the Higgs boson. You hear anything coming out of CERN? They use particle accelerators, where basically the job is to get the particle moving really, really, really fast and then slam them into each other. I highly recommend checking out the TED Ed video on how they work. But for its basic one, typically what you'll have is a loop. Okay, and at some point in the loop, they're going to have an electric field, something similar to this, to speed up the particle. Okay, they'll use that electric field to accelerate the particle. Then, all along its path, okay, magnets make particles move in a circle. So they use magnetic fields to control the particle and control its path through this particle accelerator. And by using them in combination, we can get particles to go straight or bend or move in exactly the way that we want. Okay, so if you were designing something like this and you had a proton moving at a speed of 5 times 10 to the 4th meters per second to the right between two parallel charged plates, as shown here. The electric field between the plates is 2 times 10 to the 5th newtons per coulomb. I'm going to go ahead and draw in that electric field. I will draw it in little small yellow highlighters. So electric field lines point away from positive and toward negative. So there's my electric field, okay? Electric. And then it also has, we want a magnetic field so that the electron will continue. Oops, that is a typo. That should say proton. Proton, okay, because it's a proton. So that the proton will continue in a straight line. Well, let's go ahead and look at its forces. Okay, we have our proton. Okay, it is going to be repelled from the positive and attracted to the negative. So we know we have an electric force pointing down. So we need our magnetic force to point up so that it'll go in a straight line. So we get out our right hand. Okay, we put our thumb in the direction of the velocity, our force F finger in up, okay, toward the top of the page, towards that positive plate, and our magnetic field line is going into the page. Okay, so the magnetic field is going into the page. Okay, so magnetic field is going into the page. We know the direction. Now let's figure out the magnitude of it. Okay, we know its velocity. If we wanted to go in a straight line, then we know these forces need to be equal. Okay, so sum on in, we got QVB and QE. The Q cancels, so we don't need to worry about that 1.6 times 10 to the negative 19 coulombs of charge the proton has. We want to know the magnetic field strength, so it'll be the electric field strength divided by the velocity. Throw in our numbers. And we get, is this just 20 divided by 5? Pretty sure it's 4, but I'm going to plug it into the calculator anyways. Okay, yeah, it's 4. Okay, 4 Teslas. Okay, cool. Okay, cool. One more apply on that. A particle with a charge of negative Q, negative particle, is shot into a region that contains an electric field, okay, perpendicular to a magnetic field. They give us the strength of the field and what must be the speed of the particle. Okay, it is a particle. We can see there that it's a negative particle. They go upwards. They flow against electric field lines. So the electric force will be directed up and the magnetic force will be directed down. And then setting those forces equal. We've already done this a couple times, so I'm just going to jump straight to the, we'll show it one more time. Why not? Okay. The velocity is the ratio of the electric field strength to the magnetic field strength. So it just becomes a very straightforward problem. Once we know that, we got the velocity is 2 times 10 to the 4th newtons per coulomb divided by 0.5 Teslas will give us 2 times 10 to the 4th divided by 0.5 gives us 4 times 10 to the 4th. Did I need to plug that into my calculator? Probably not. But 4 times 10 to the 4th meters per second. Okay, cool. Okay, cool. So, what about a wire? Okay. Well, okay, if we're thinking about the current in the wire, okay, if this current is going down, okay, you can either think of that as the flow of negative charges, the electrons going up like it actually is, but we can also model current as the flow of positive charge. So if you have current flowing in a wire, you have a lot of charge flowing. So if we put our thumb in the direction of that positive charge flow and our finger in the direction of the wire, we get that there's a force outward, okay? And we can find that force with respect to the current, okay? So we know the magnetic force on a moving charge is QVB as long as they're parallel. And then the Q that is moving there is the current. And current is defined as the flow of charge over time, okay? So plugging in some of that into here, I'm going to plug in that charge for the current relationship for that charge. So we have current times time. Okay, velocity, I'm going to go ahead and write as distance over time times b. And you can see here that the time and time cancel out. But then we have this distance. And the distance is from that velocity component. So that distance will actually be the length of the wire in the field. Okay? Length of wire in the field. The distance that the positive charge would flow, that current would flow. And indeed, that is how it's written on your equation sheet. The magnetic force on a moving particle is equal to the current times, want to make sure I that I put it in the same order that it is on your equation sheet. So it is the current times the length of the wire. And then just like in the other one, it is a cross product. Okay? A cross product. So in reality, how we end up using this equation most often is IL sine theta B, where the magnetic force, I is the current, L is the length of the wire in field, and B of course is the magnetic field, and theta is going to be the angle between the wire and field. Okay. So let's go ahead and apply that sum and find the direction of these forces. Okay, you can put your thumb in the direction of the current, okay, the direction of positive charge, the direction that charge is moving. Your fingers go in the direction of the magnetic field, and as I'm doing this, the force is going into the page. Okay, again, make sure that you're doing these hand motions on the plane of your computer screen or the plane of your paper, wherever you're working on this on. So on this one, the magnetic force, it would be zip, zip into the page. Wait, can you get your magnetic field and your finger to go in the same direction? Okay, no. And if the velocity is parallel to the field lines, you have no force. Okay, because the length is parallel to the field. Okay, so theta would be either 0 or 180, depending on how you're looking at it. And sine of that is 0. Okay, so let's go ahead and apply this a little bit. A wire carries a current of 22 amps from west to east. Okay, great. More north, south, east, west. So let me go ahead and draw it in. Never eat shredded wheat. Okay, and it's carrying a current of 22.0 amps from west to east. Okay, so there's my wire. Assume the magnetic field of Earth at this location is horizontal and directed south to north. Okay, so we got the magnetic field lines. Okay, and has a magnitude of 0.5 times 10 to the negative 4th Teslas. Find the magnitude and direction of the force acting on the 36-meter length of wire. So the length of the wire is at 36.0 meters. Okay, the wire is perfectly perpendicular to the field, so we can just use the equation in the form ILB. Okay, it's perfectly perpendicular. You're going to have that max force. So we just got to plug in all our numbers. 22 amps times 36 meters times 0.5 times 10 to the negative 4 Teslas. Can you guys think of a scenario where you might have some high current running for 36 meters in Earth's magnetic field lines? Telephone wires, okay? Power wires. Those are the example of this. So you get 3.96 times 10 to the negative 2 Newton, or 0.0396 newtons. Okay, cool. Okay, cool. And I just realized that this problem, we do not have enough information to answer it yet. Okay, so we're going to go ahead and skip it for now. Okay, that'll be coming back in our electromagnetic induction lecture. And that brings us to, how does a motor work? Okay, to do this first, I want to show you how it works. Okay, so this is the world's simplest motor. Okay, what it has is it has a battery in the bottom connected to 2 metal leads. Okay, they come up through the top. And then I have a magnet that sits on top of it. Okay, I add my coil of wire to it. Now it's connected to the battery, so we do have current flowing in the wire. And give it a little, oh, don't even need to give it a little push to get started. It is already on the roll, okay? So why? Okay, I have current in a magnetic field, and that is what causes this rotation. Let's look at it a little deeper back in the notes. Okay, so in this motor, okay, we have a coil of wire, and then we have current flowing. So using your right hand rule, okay, put your thumb, we got the force. So on one wire, we see this force going in that upward direction. Okay, we have that magnetic force. Where here, where we have the current flowing in the opposite direction, the magnetic force is directed downwards. Okay, and it is that tilting of it that causes the rotation. Okay, but that would cause it to just zoop and stop, but instead it keeps rotating. Why? Okay, well, here it's because of something called a commutator. On this coil for the world's simplest motor, I cheated it by sanding off half of the insulation on these wires. So as it was spinning on these leads, okay, see if I can get spin again. So what it's doing is it's turning on and off as it spins. Where it's something like this, they use a commutator connected with brushes to the circuit. So when this coil spins, okay, you can picture that eventually, as this one goes down and around, this is going to go down and around, and it is going to flip the direction of the current. Okay, as the coil turns, the direction of that current flips, and thus the forces flip, and it keeps going in another direction. Now, in an actual motor, this is the inside of a hobby motor. So in it, you can see the coils of wire, and then all around here, this area is the actual magnet itself, okay? See, it's a magnet, it sticks to things. So it is these coils of wire, okay? You can see there the gaps in the metal discs acting as that commutator that allow it to spin when you connect it to a battery, okay? And yeah, okay, cool. So that's how motors work. And we can also calculate that amount of torque that it experiences. So say we have this rectangular loop of wire here. It has the current. I'm going to be drawing in the current in green. So the current is going up in that direction, in this direction, and there, and up. Okay, So what's going to happen is that the magnetic field is pointed to the right. So on the top wire and the bottom wire, there is no force, okay? There's no magnetic force on the top or bottom wire. However, if you look at this wire here, okay, thumb up, direction of the forces, it has a magnetic force going into the page. So on that wire, the magnetic force is into the page. Where on this wire, it's going the opposite direction. So the magnetic force is out of the page. And that will cause this to rotate, okay? It will rotate about this axis, okay, as this one is pushed down and around and that wire loops up, okay? So it's rotating around in on itself like that. I know that's a little funky with how these incoming wires are drawn, but just ignore them, okay? So how much torque does that experience? Okay, you might remember from AP Physics 1 that torque is the radius perpendicular to the force. Okay, now zoom in here, the radius of the rotation will be L2 over 2. Okay, this is the radius of rotation, which we can then write as L2 over 2. Yep, because that's the axis it'll rotate on. And then if we look and kind of zoom in on this top wire, okay, and treat it just as one pivot point there, it is the whole coil that is rotating, okay? So that force is being applied on the whole side. But if we consider it just like that, that force is the magnetic force, and we can use ILB to determine its strength, okay? So we have I, that is the length of the wire in the field, so that will be L1 times B. Now, note, okay, since it's rotating, and you might have learned it with a door handle where you have one point of rotation and one force. Here we have a point in the middle and two forces, okay, a force up and a force down. So that force is applied on both sides, so you can think of the torque as twice that amount of force. Okay, so the total will be equal to 2 times that amount. Okay, so 2 times L2 over 2 times I L1B. Well, obviously the 2 cancels out. And then, hey, wait a minute. We have here, okay, L1 and L2. L1 and L2. Length times height times width. What's another word for that? The area. And that is one of the other equations for calculating the torque on a coil of wire in a magnetic field. Okay, so this can be used for calculating the torque on a coil in the field, in the magnetic field, where T is, of course, your torque in Newton meters, I is your current, A is your area in meters squared, current is, of course, in amps, and B is your magnetic field strength in Teslas. Yep. So using that equation, grabbed a problem from the textbook. I haven't seen this one used in the AP Physics 2 curriculum in a while, but it is within the realm of things that could come up. But since we don't use torque that much in AP Physics 2, it's more of an AP Physics 1 concept, it is a little bit less likely, okay? So let's think of this one here, though. We have a coil of wire that has an area of 2 times 10 to the negative 4th meter squared. It consists of 100 loops, so times 100, and it contains a current of 0.045 amps. The current is placed in a uniform magnetic field of 0.15 teslas. Determine the maximum torque on the coil of wire. Well, we know as it spins, it'll go through max and min as that area is perpendicular to and then parallel to the field. Okay, it doesn't say the direction of the current or the magnetic field, so I'm not going to worry about it too much. Okay, we just know we have a coil of wire, okay, in some magnetic field. And we can find that max torque using the equation that we just derived. Torque equals IAB. So 0.045 amps times the area. And since there's 100 loops, we multiply the area by 100 times the magnetic field strength to get a max torque of 1.35 times 10 to the negative fourth Newton meters. Okay, cool. That's it for magnetic force.